Today. It's a great pleasure to have Yassine Tahraoui today from Center for Mathematics and Applications, Nova Math, from Portugal, and he will be talking about stochastic 3D grade for fluid equations. So Yassine, it's all yours.
Assalamu alaikum. Thank you very much, Sharon, for the introduction, and let me thank the organizer for this opportunity to talk a little bit more about my work. It was a bit forced because there was like some things, but it's always good to give a talk in front of such a very nice audience. So what's my plan today? I will try to tell you something about non-Newtonian fluids, and more precisely, I will talk about third-grade fluids equations. This will be my main interest in this talk of this afternoon, and this will be particularly in the second part of talk. So, following the tradition of TCMS seminar, the first part should be an introductory part. And for that, I will try to tell you something for evolutionary stochastic PDEs. So generally, the approach that I'm using to study my problem are coming or motivated by some approach in the deterministic theory. So I will tell you a little bit about the main machinery or on some differences and some issue that you should take care in consideration when you consider stochastic PDEs. So what are generally the questions that you are interested in? So given a stochastic PDE is, we are trying to understand if the solution exists, and if it exists, in which sense we are understanding our solutions. Once we can understand that you have solution, you are interested is we can have a unique solution of our problems, and then what is the relation between this solution and the data that you have. The data could be the initial data or some external force, and in the case of a stochastic presence of some stochastic, even the relation with presence of certain Brownian motions that can appear as a force in my systems. And also in the direction of some qualitative properties, we can understand some asymptotic, basically large time behavior or stationary solutions, and also what is the impact of the presence and the absence of noise in our system, which correspond what it is now on our large deviation theory. Concerning the large time behavior, I am more interested in the invariant measure quotient and the ergodicity. And you can see stochastic PDEs or stochastic evolutionary PDEs as a dynamical system where the state is infinite dimensionals. So I will back to that later on. We are interested in other questions, but basically in this talk, I will be talking about the point that appear in blue colors. So as I mentioned in the beginning, this talk will be in the two parts. The first part will be a kind of introductory part. And in the second part, I will tell you about some contribution and results we established in collaboration with Fernanda Cipriano from Universidad Nova de Lisboa. And it concerned the local well-posedness of some third-grade fluids and also some ergodicity results for some subclasses. So let me start with some basic notions. So to be sure that you are speaking the same language. So in my talk, when I say omega FP, I'm considering complete probability space in the sense that my sigma algebra contain all the set of zero measure with respect to my probability measures. And then when I say in E, separable Banach spaces. So there is some basic definition. So I assume that all of you know what does mean a random variable. It's just a measurable map from the set omega unto the sigma algebra F taking value in basically separable Banach space E. You can think, for instance, E to be the real numbers with the Euclidean. A stochastic process, it will be a family of indexed random variables. And therefore, I can see also, since I have family indexed by two parameters, omega and t, I can follow the map that t associated what we call the path, and I can talk about the continuity. An important notion in this field of stochastic calculus is what we call then filtrations. A filtration is a family of sigma algebra that is increasing over time, and is somehow It's contain the history of your phenomena. And it tell you how the history of your randomness, if you want, if omega interpret randomness in system, is if evaluate or increasing over time. This is very important to construct what we call a stochastic integral that I will speak in a moment. So when I say some process is FT adapted, is like you should see the measurability of such parameter every time you fix this parameter t, and you can think that to be the time that you see the measurability with this small sigma algebra. So you are like strengthening the measurability that you have initially about your measurability that you assume when you talk about random variables. And since I am interested in stochastic PDEs, it's preferable to talk about the sigma algebra of predictable process, which is some sigma algebra generated by the product of this FT adapted process with some sigma algebra in the time interval st. So a particular example, if you have some FT adapted process which are continuous in time, then this kind of process are predictable process. So this is this class of process that will appear in my talk. So a probabilistic motion is an essential object that appeared by many physical motivation, and it's really discovered by the botanist Rupert Brown after certain experiment, and the name comes from there. So it's just a continuous process that starts from zero, and when you see the increment is independent of the sigma algebra generated up to the time s. And as a law, it follows the normal distribution with a zero mean and a variance t minus s. This is, I'm talking about a real valued Brownian motion. So what is interesting about this object is the following. You can prove that this Brownian motion are almost continuous, and moreover, its holder with some exponent gamma, for gamma between 0 and half. And I want you to keep this information in your mind when I will talk after a few minutes about stochastic integration. So keep this information please in your mind, that it has just a regularity with some holder continuity and maximal to 1/2, and it doesn't reach 1/2. Another important thing is that the quadratic variation of such process is finite.
Yassine?
Yes.
Yes, sorry, my mic was not working, so I was asking. So what is, if you go back please to the previous slide?
What?
So yeah, so the graph here, how is it relevant to what you are defining here? It's
Oh yeah, my graph. This graph is just one trajectory, one sample trajectory. So if you see the map for one realization, you will have such a realization.
Okay, so what you want to say is that, so this graph is more or less a graph or a function which is not
no, it's not function. You see this omega, this Brownian motion depends on t and omega, right?
okay.
So this omega lives on some abstract set omega where you have your event sigma algebra.
Okay.
So if you fix and you follow only one trajectory, one sample path, one trajectory, you will have such realization. But this doesn't tell you all the information about your distribution, because your distribution is a normal distribution with zero mean and variance t minus s. In other sense, if you want, if you, for example, wanted to draw 1,000 realization of these Brownian motions, you will have different graph. But what is important is if you see the mean, you will see the zero, like the map y equals 0 is the mean, and all the graphs with almost probability 1 will be between the square root of t and minus square root of t. So this is what I tell you, the variance.
So the equivalence in your last statement there should be understood in that sense. So the difference is
what is no, this is not equivalence. This is does mean sorry. This does mean it follows the normal distribution.
Okay, all right. Okay.
The difference of two objects, and you know, normal distribution is from this Gaussian kernel. When you have these Gaussian kernels, so you have the mean and the variance stuff that appear there. So I mean that when you see this random variables for t and s fixed is a random variable that follow the normal distribution with a mean 0 and the variance t minus s.
All right, got it. Yeah. Okay.
I'm sorry, I mean I didn't mention, but it's just one realization. Maybe in my slide you will see better, because I have a graph that I wanted to share. Okay?
Yeah, perfect. Thanks.
Okay, so I was here. So what's another property is that if you prove that the quadratic variation is finite, then you can deduce that the variation is infinite. And keep also this information in your mind. So I will make some comment about that. And therefore, you can prove that with the probability one, the graph of Brownian motion, when you see as you see it, I mean, if you're familiar, for example, with this kind of Fairtrust function and whatever, is something similar, is nowhere differentiable. And as I mean, maybe I can assess some link because it looks, maybe this kind of result looks strange for me, but you know, for example, if you take the space of continuous functions and you see the set of continuous functions that they are nowhere differentiable, you can prove that this set is dense with respect to the topology of continuous function. It's really strange, frankly. Strange, I mean, looks strange, but it's like that. So it's something normal. It's not that strange in this sense. So let me tell you something about the construction of stochastic integral. So considering some Hilbert, separable Hilbert space, and you consider a map that you have your time interval, I will denote E, and you have your set omega, which is abstract, where it's expressed the randomness. You can see a map from this takes value in some Hilbert space. And then you can define some elementary process in the following sense. By elementary, you have some coefficient that live in your space H, and you have this characteristic. What I am assuming elementary is that when you take this element G, it will be FTG measurable. So you see the starting point in your time interval. I am asking measurability in this sense. This is what I mean by elementary. So the first step, I will construct an integral as standard way, like you do in Lebesgue or whatever. I can define an integral as just as summations. And this is well defined. Then the question will be, in which up to which class I can extend these definitions. And for that, you can prove the following isometry, which give you somehow a relation, but when you take the expectation, which basically an integration over all the possible outcome with respect to your probability measure, and you take the square inside, you can have some integration with respect to time, instead integration with respect to this Brownian motion that I just defined for elementary process. This result is true. And basically, how to prove this result, the idea is you use the property that I told you in the beginning, that this Brownian motion has an independent increment. You do some computations and you will arrive there. So this is the K ingredient, is the independent increment. And therefore, you can prove that this result that I'm mentioning is correct, is true for class of elementary process that I mentioned. Then what you do, that following by some approximation or density argument, you can extend this definition to a reasonable class, what we call the class of predictable process that I mentioned in the beginning, that I told you it will be a convenable to solve some SPDs in this setting. You can do as you have in your mind, same idea like we do in the construction of low-peg integral and other stuff. You define sequence, and you are in some complete space, you consider some Cauchy, and you consider the limit, and so on and so forth, and you do such constructions. What is important is what is the properties that you get from this construction. You can prove that for every element in this class of functions, you keep the property that we call a martingale property, and in the sense that if you take the expectation of stochastic integral with respect to this Brownian motion, then the integration over all the possible outcome is 0. You can prove also that your isometry is still held by some density argument, and therefore, when you see the map, if you give me some integrand that have the desired measurability issues, this predictability, and you see the stochastic integral that just constructed, it's well defined, and this map that consider the integration operator is a linear and continuous thanks to this isometry. So this is the general idea how to construct stochastic integrals. It's quite similar, but maybe the only thing that you should keep in mind is the measurability issues, and there is some particular regime of measurability that you should consider to define in somehow correct way this stochastic integral. A common thing is when you do computation, you are talking about chain rule. So generally, when you have function and when you compose by another function, you have a formula how to compute the derivative of the decompositions. So you have something similar in if the process is more contain stochastic part. So imagine that you have certain process that have a deterministic part, and you have this part in the presence of some Brownian motions. It turned out that because of this property that I mentioned, that the quadratic variation is finite, then when you do a chain rule, or what I will call Ito formula, you should have an extra term, Ito correcting term. So in comparison with the deterministic chain rule that you have, when you do stochastic calculus, and basically when you consider some process that they have this form, something against dt plus something against a Brownian motions, you have always an extra term, and you should take this term in consideration when you perform such analysis. So this is a good point that I want you to keep in your mind, and I hope so. So, okay, just as an example, if you take this process that I am writing here, do sum of two elements. So if you are interested to take the absolute value square multiplied by some function, then you will have the following formula by applying Ito formula. So the term that multiplied by c is just the time derivative term that comes from the exponential, but the beta square term is the corrected term I was talking about. Okay, so all these things are basic, so I hope that I give you good motivation, and if you don't know about this, so go and try to learn about that. So let me now talk about more things that are related to my talk in the second part. So when you consider an evolution problems, there are many things, but let me insist on 2 or 3 basic things. A first ingredient is what is called Lewis-Gelfand trouble. Lewis-Gelfand trouble is just trouble, and you can think about a Banach space that impede continuously and densely in certain Hilbert space that you can identify via its theorem with its DL, and then you have the DL part. And for example, you can think about certain Sobolev spaces. And then if you define certain operator that acts from V to its DL, if you are in the correct framework and if you take a reasonable external force, then you can prove the existence and uniqueness of the solution of the problem that I denoted by 1 and 2. So what I wanted to say here is the following. You have different approach to do it. This depends on how your operator A looks like. So if you are in the situation of ordinary differential equation, then you have many ways to do it. If you are in linear PDEs, then you have a male solution semi-group theory that you can use it. If your operator is a monotone, then you have the theory of monotone operator developed by Lyons, and you can do such things. But what I wanted to say is, generally, these operators are nonlinear, and generally, you need to have some compactness argument if you have some regularization where you know that how you can solve the problem, and basically have in mind some finite dimensional approximation. So I'm underlining the word compactness. So you need to have some compactness argument and result to solve such problems. So what I do mean by compactness argument. So when you approximate your program, then you perform some result that you are familiar with. You can prove the existence of either regularized solution or approximate solution. Then you wanted to pass to the limit with respect to the regularization parameter or approximation parameter. And you need to have an information about your solutions. You go to your equation in the deterministic theory, you use admissible test function. You have some information about the integrability or some information about your solution that he is living in some Sobolev spaces. Then a second step is you use your equation, and basically number 1, to have an information about the time derivative of your solutions. You gather all this information together, and therefore you can call some result of compactness that can give sense to the trace in time and solve your problem. So this is the general strategy.
Can I interrupt you? before you go further, can I interrupt you here? Yassine?
Yes, yes.
So this is just a formal statement of a theorem, right? So it's
Yeah,
because
I don't want it to be precise. I don't want it to
yeah,
be precise.
because
I try to explain an overview.
even if A is a smoothing operator, I believe you cannot catch a solution or construct a solution which is continuous in time or bounded in time with values in V if your initial data
Yeah,
is
yeah. I'm coming in that to the next slide.
okay, sorry. Okay, go ahead. Sorry.
Okay. Thank you, Aaron. Thank you. Okay. So yeah, so this is of course I said under suitable assumption on A. So just trying to explain the idea of compactness. And I'm in the next slide, I'm saying what is important. What is important is you need to precise what do you mean by solution to your problem. And basically you need to have certain formulations that I am written in the first block. But then the question that you should ask, do I have the right to write such a formulations? Yes, you have the right to write such formulation if you have the correct information about your solutions. So for instance, if you know that your solution is in some Lubeck space in time with value in some space V, and the derivative live in the DL of such space, then you have some interpolation results that tell you this space is unpit continuously in the space of continuous function with value in your middle space H, value in H, and you have an integration by part formula. And particularly, if you differentiate the square of the norm within the Hilbert space H, then you have the following duality almost everywhere in time. This is somehow standard results. What I wanted to say here, if you don't have this information about the regularity of your solution, all this thing that you are writing here has no sense. So what I wanted to say is when you see your map from the time interval 0t takes value in some Banach spaces is not an easy issue. So we are, in which sense you understand the time derivative? Typically, we understand the time derivative in weak sense or distributional sense. Then the question, you need to know how to deal with the distribution with value in vector spaces. And if you are familiar a little bit with this theory, you need always to have a pivot space to define such weak time derivative. If you are not in the frame of Lyons-Gelfand trouble, then you may face same problem. Another things, when you consider these vector spaces of the type LP0TV or V8 some Banach spaces, generally these spaces doesn't catch or doesn't keep the Radon-Nikodym theorem that it's a crucial theorem to prove, for example, a duality between Lubeck spaces. For example, if you wanted to prove that the DL of LP is LP prime, where P prime is the conjugate of P, then you need to call at some level Radon-Nikodym theorems. And keep in mind, for example, the issue that you face if you wanted to see the duality between L1 and L infinity, you have some problem. You have some duality in some sense, it doesn't happen in other sense. And this because you have some problem with Radon-Nikodym. So the difficulties, it's quite similar when you deal with vector space, this space of type LP0T with value in some Banach spaces. So I am saying that just like to motivate your understanding of the problem. There is many difficulties that we should be careful when we do such manipulation. So it needs a lot of attention because there are many deep information that maybe we don't pay attention when we're dealing with sample situation. But when if you want to study your problem in correct way, then you need to find many things and you need to give sense to it. And the situation became more complicated when I am going to my stochastic part. So these things are known in PDEs theory. So now let me try to go a little bit in the stochastic part of the deterministic part that I just mentioned. So keep the same setting of Lyons-Gelfand trouble and add a complete probability space to add some randomness to my system. And the presence of my randomness will be given by the equation given in 4. So we will have some drift, depends even in my solutions against some Brownian motions. This writing is a rather formal writing because, as I told you, this object is nowhere differentiable. So the differentiability doesn't exist, but this you can give it sense when you integrate over time and you understand the right-hand side of 4 as an integral in 8 or 10. Then it gives sense. So this is the sense or the precise set that you should have in mind about the writing form. So just I wanted to explain the idea that's in comparison with the last slide. So when you construct solution of this kind of problem, basically you construct solutions in integrable form in time. So you will define a solution in the following sense. You will consider an integral over time, and you ask your solution to satisfy certain regularity that gives sense to the integral where your operator acts in one, and it gives sense to your stochastic part for every t in time intervals. And of course, by conclusion from your equation, you will have your solution to be continuous in time with value where the right-hand side is level. But if you study the regularity of your solution by using this, again, Newton-Gelfand trouble arguments, you can deduce some continuity with value in the Bivo space somehow that I am mentioning here. And of course, I am mentioning what people generally, when you do PDEs, you have what we call energy equality or energy inequality, which formally you take your system and you test against the solution and you try to see what you have as equations. So in the stochastic part, you will have the last part, which is the coming from the stochastic part, and you will have the correction term that comes from E2 formula. Then, of course, depends how operation is, you can have some term. For example, if you have a Laplacian, then here you will have minus Laplacian, then you have the norm of the gradient in L2 square, and so on and so forth. This is how generally you understand the solutions. So let me tell you why you should understand your solution, or in this sense, because as I told you before, if you go back to this equation and you try to do formally the time derivative of u, then the time derivative of u will be the operator part, which fine, but you will have dw over dt. And remember in the beginning, I told you that the regularity that you know about w, it's a Hodder continuous with at most an exponent alpha less strictly than half. So formally, if you take y derivative, so we are dropping in the space of distribution, which basically the deal of C1 alpha, which basically something C minus alpha. And therefore, you are not dealing with any integrable function anymore. It's just a general distribution. So you don't catch such information when you do a stochastic PDEs. So this information about Lewis-Gelfand trouble somehow, let me say, fell in some sense. But you need to find the way to fix this problem if you wanted to keep your approach going on in this setting. Okay, so I will say more about that in maybe you will see that in the second part. So just here I want to say there is a relation between the deterministic and the stochastic part. So if you consider some stochastic PDEs and you consider initial data which are deterministic, the operator that lead in your system in the PDE is linear, then you can prove that the deterministic solution coincide with the mean of the stochastic solutions, as I am writing here, because the expectation is a linear part. So this is somehow generally some link, but generally we are dealing with a nonlinear, so the relation is more complicated and sophisticated to establish. Okay, so what I said up to now. What I said up to now, that when you solve an SPDEs, you have some nonlinearity and you need to do some compactness. But to do some compactness with evolutionary PDEs, you need to pass by Lewis-Gelfand trouble to use some distribution with value in vectorial spaces. But unfortunately, having information about time derivative is quite complicated, and you don't know how to do it, how to fix it. Of course, following the chain rule, if you wanted to do information about your solution, you don't use a test function method anymore. You need to perform E2 formula, and E2 formula requires something. So you need to be in the correct framework to perform some computations. And when you have presence of stochastic forcing, the information about time derivative living in some integer in time is not available anymore, and this interpolation is not correct anymore. And the formulation that I wrote in the deterministic setting, it has no sense, at least up to the information that you have from here. Another thing is when you have a stochastic integral, you are not just looking for some solutions that are measurable with respect to sigma algebra, but you are looking to more fine property, which is a measurability that change over time. And at every instant as you need to that, you have this measurability. Otherwise, your stochastic integral is not well defined in the sense that I precised in the beginning, in the sense of E2. So this is an extra difficulty that you should keep in mind when you deal with such problems. So since my approach in the second part will about stochastic compactness, let me tell you about what I mean by stochastic compactness. So basically, if you take a function in the deterministic set and you have function that physically depends on time, which is t, space x. But when you are in the stochastic framework, you have the extra variable omega. What is important that you should notice that when you deal with a physical problem depends on t and x, you have implicitly a topological structure that appear in the time interval or your physical domain, and this helps you to define what do you mean by differentiation, how to differentiate a function living in x. You know, you do this translation and you do the fraction and you consider the limit. But if you have just an abstract set, this manipulation is not correct anymore. If you wanted to have some information, you can't derive. What does mean deriving with respect to omega? It has no sense. Of course, there is another way to see things, which is I don't have experience about that, but some people do Malevin calculus that see some correspondence and try to define some differentiation in some sense. So my aim is how I can deal with such problem if you wanted to adapt my approach that I am using to solve PDE to solve NSPDEs. And then this leads me to define to you what I do mean by stochastic compactness in my sentence. So generally, when you do deterministic PDEs, as I mentioned, you have time and space variables. So if you have information about the function time derivative, use the famous approach of Lima of Aubin-Lyons-Simon, and you have some compactness to give some sense to have some strong convergence and also to have some trace in time to do these manipulations. But when you have this omega and omega is just set, how to fix that or how to solve such problems. And the idea is the following. I don't consider u as a function of tx omega, but I will more focus in the law of such function u to x omega, which is a random variable or stochastic process. When I see its law, it can be interpreted as a probability measure on some Banach spaces. And to carry on my argument, I will work with this probability measure instead of working my solution and catching information about the law of my solution. I hope that I can catch information about my solutions. So how I define the law is just given by the following sense. The law of a random variable taking value in some Banach space is just the probability of such element belong to any Borel set where my solution lives. An example of set E that may appear, you can see is where your solution lives. If you forget about the randomness, it may be the space of continuous function with value in some Hilbert space. It may be the space L2 and this kind of space. So when I talk about stochastic compactness, I will basically talk about compactness in the space of probability measures. So I use compactness machinery from the space of measures. And this leads me to define or to introduce some well-known result and very, very powerful tool. So if you take a topological Hausdorff space and you put sigma algebra generated by the open sets, then you can talk about the tightness, which somehow express the compactness of this family of probability measures. So if you can find the compact set in your topological space such that you have an estimate or basically your family of probability measure is concentrated somehow in this compact set almost with probability 1, then this family is tight. Then there is another theorem that it's Prokhorov. If you ask your topological space to Hausdorff space to be more regular in the sense it be separable metric space, then you have the following equivalence. If you take a collection of probability measure defined on this separable metric space, then you can have the following equivalence. If this family is tight, then you have that this set is a pre-compact in the space of probability measure, which tell you that you can extract subsequences that converge weakly with respect to a such topology in this space, with respect to the weak topology in the space of probability measure. This is a theory has nothing to do with stochastic PDEs, but the next theorem has to do. There is a score code representation theorem. If you have probability space and you have a family of random variable takes value in some separable metric space, and you know that the law, which is a probability measure, is weakly convergence, and you can get such information for subsequences if you have tightness, then you have the following representation theorem. You can find a new probability space and the new random variables defined on the new probability space such that the law of the new random variable equal the law of the previous one, which is important. But the strong information that you get is the following. You have almost surely convergence with respect to the new probability measure in the space u1 times u2 of a new random variable, which somehow strong a little bit to solve your problem. And this important is very important, and I will use it in my second part. So this is the statement of such theorems. I want to just to recall it. So let me conclude this part by showing you this. So Harun in the beginning told me that when you see the graph, it's graph function, but I just like drop one realization. So when you see, for example, you can do one realization, you can do 100 realization, 1000 realization, and here, for example, it's 1000 realization of trajectories of Brownian motion. What you can see here, the trajectories are different, but as I mentioned in the beginning, they are concentrated over the mean, which is 0. And if you draw the square root of t and the square root of minus t, which is the variance, then basically all the possibilities are in between. So this is 1000 realization. So of course you would be more interested in these distributions. So having this picture in mind, when I will talk about local solutions, please have always in mind the following. So if I take just a very, very stochastic, simple example of stochastic ordinary differential equation. So we take an ordinary differential equation where the solution is an exponential, and you add some constant multiplied by dWt, then you can use Ito formula and you write explicitly the solutions. So you see from the different realization of Brownian motions, you can see that you will have a different realization of your xt. And therefore, when you talk about local solutions, means a solution that lives up to certain time t, then you see that your value of your solution will be not the same because it depends on the trajectory. And therefore, the correspondence, what is corresponding to the local in the deterministic theory, it will be certain things that I will call stopping time. So, and this stop time should respect certain things that I will talk about in the second part. And this basically because of this realization that you see here. So somehow this will help in some sense to understand why when I talk about the definition of local solution, I will ask certain thing. Maybe for someone outside of the field, it looks strange, but this is somehow, it helps you to understand it. So to finish this part, I want to just to mention some reference for interested reader. Classically, you can use the books of Daprato and Zabitschek to learn about stochastic PDEs, basically the linear one, and take the different notions. If you are more interested also in the nonlinear one, you can check the books by Privo, Ruckner, and Deliu, about where the books are about how to solve a monotonous PDEs. So basically how to adapt this technique of Lyons-Gelfand from a deterministic to the stochastic, and they are, from my experience, they are good to learn some stuff. If you wanted to learn about stochastic compactness, of course, there are many references, but I would prefer this paper that I mentioned by Givalli and Alexandra Zimmerman, where the paper is very well written about using the machinery of stochastic compactness to prove the well-posedness of some SPDEs where the operator is pseudo-monotone 1. So thank you for your attention, and that's all for the first part.